So, okay, hello everybody. Today we are very happy and honored to have with us Dr. Yannis Zouganelis, and I would like to say a few words about our speaker today. So Yannis got his bachelor from our department, the Department of Physics at the National and Kapodistrian University of Athens 20 years ago. And then he went to Paris for his master's thesis and his PhD. After that, he spent 3 years at the University of California in Berkeley, California, at the Space Sciences Laboratory as a postdoc, as a research fellow. After that, he moved back to Europe and was for 2 years a research fellow at CNES in Meudon, France. And in 2008, he became an associate professor of astrophysics at Sorbonne University in Paris. Since 2014, he is the Solar Orbiter Deputy Project Scientist for the European Space Agency, and he's based at ESA in Madrid, Spain. So naturally, he will be talking about Solar Orbiter, about the Solar Orbiter mission. And since November 2020, he's also the head of the ESA Science Research Fellowship Program. And Yannis is also an associate editor for Astronomy and Astrophysics. So again, we are very happy to have Yannis with us. Thank you for accepting the invitation. And you have the floor. Take it away.
Thank you very much, Yanni, and thank you for inviting me, actually, because this is the first time I will be giving a seminar to my alma mater. So I think it's great, and actually I'm very stressed because you know, I still see one of my professors in the participants list. So well, you know, for me a professor is always a professor. So I'll be a bit stressed. So please forgive me about this. So let me share my presentation. So can you see it full screen?
Yes, it's full screen now.
Okay, great. So as you said, Yanni, I'm the Deputy Project Scientist of Solar Orbiter at the European Space Agency. And before I go to the slides, I would like to say what a project scientist is. So actually, it's a very specific role that we have at ESA and at NASA. Actually, 1 or 2 persons that are called project scientists for 1 or 2 persons per mission. And this is, so our job is to coordinate all the science that the mission does. And we are not doing the science ourselves, so we are not the ones really analyzing the data or writing the papers, but we are there to ensure that we get the maximum output from the science point of view out of a mission. So, and we are there before, during the development phase of the mission, and we are there after, during the operation. So from you know, from the birth of the mission, from the adoption of the mission, down to the very final steps of archiving. And we really coordinate. We are the interface between the entire science community and the people who build the spacecraft, who build the instruments, and who operate the spacecraft. So just for you to understand what my role is at the European Space Agency. So now let's go to the presentation itself. So just a reminder of what ESA does. So ESA has many solar system explorers, and Solar Orbiter is just one of them. So I'm sorry I cannot use my mouse with the keynote that I'm using, but I will just guide you on the different parts of the slides by just telling about them. So Solar Orbiter is yet another solar mission, I mean, the most recent one that came to to be added on this slide. Where you see in the middle of the slide the active missions, the missions that are currently on operation in the solar system, and these are Solar Orbiter, Proba 2, SOHO, Hinode, IRIS, all these are solar missions. Then we have Bepi Colombo that goes to Mercury. Right now, we still have Cluster for 20 years, which is the Magnetosphere Plasma Physics mission. And we also have Mars Express and ExoMars. And in the future, we are going to have all these missions that you see on the top of the slide, and including Envision that was just selected 2 weeks ago to go to Venus. So we have some missions for almost the entire solar system, except for Uranus and Neptune. So this is for the solar system, and this, of course, is doing also the astronomy missions. And now this is not as a function of distance, but it's as a function. It's in the spectrum, and the biggest missions that we are waiting for. The big mission that we are waiting to be launched at the end of this, in the few next months, is JWST. That I'm sure there are many of you participating in it, and yeah, next year we also have Euclid, and also from the solar system we will have JUICE getting launched. So this is just a very brief overview of the missions that the European Space Agency is doing. And now let's go back to Solar Orbiter, our mission. And this is again not the first solar mission that ESA is doing. And we did have 2 past very successful missions that were Ulysses and SOHO. Ulysses, so both of them in collaboration with NASA, just like Solar Orbiter. So Ulysses was the first mission that got out of the ecliptic. So the ecliptic being the plane where the planets are, and it went over the poles of the sun. So there were 2 big differences with Solar Orbiter. Is that first of all, Ulysses didn't have any camera, so it went over the poles, but it couldn't take images. And the other difference is that it went over the poles, but at a distance of 3 astronomical units. So it didn't really go close. So it had to go to Jupiter to get momentum to get out of the ecliptic. And so it didn't really, it couldn't go close to the sun. And the other mission was SOHO, which is still in operation after 26 years of operations. And, you know, the missions are usually supposed to operate for 2 or 3 years, but now we have SOHO operating for 26 years. So this is really a big success, a mission that really changed what we know about the sun, and it still works, but it is at 1 astronomical unit, so it is close to the Earth, so it doesn't go close to the sun. And now we are combining both. So this is what Solar Orbiter is about. So we have a mission that will go out of the ecliptic, just like Ulysses. We have a mission, instruments that can do remote sensing observations, just like SOHO. We also have instruments that are doing in-situ observations like Ulysses. So we combine everything on a single spacecraft, and on top of it, we go close to the sun. So close to the sun, out of ecliptic, remote sensing, and in-situ instruments, so everything you can imagine, and covering pretty much all the fields of solar physics. So what do we want to answer with this mission? So the big question is, how does the sun create and control the heliosphere? And why does solar activity change with time? So this is, of course, again, a very big question. This is how this mission was solved to solve many problems. And also when you sell a mission, you need to satisfy big communities to make sure that you will have a lot of outcome out of it. And if you want to learn for the exact objectives of the mission, and I will go in some details later on, you can go and read this paper that we published in the A&A special issue, where the entire mission is described and all the instruments. And so you can see there all the objectives and the entire description of the mission. So the observations we can do are, as I said, in situ and remote sensing. In situ means measuring what is happening around the spacecraft. And what we want to measure is the solar wind plasma, the fields, waves, and energetic particles as close as 0.28 astronomical units. This is the closest that we will get. So just a remark here. Many of you know the NASA Parker Solar Probe mission that goes even closer to the sun. The big difference is that Parker Solar Probe doesn't have any cameras. So really 0.28 is the closest we could get with cameras so that we don't get burned and we can still send back meaningful data. So the remote sensing instruments, we are going to observe the entire sun. So the entire sun and also high resolution observations at the specific region of the sun, depending on what we are interested in its time, invisible light, UV, and X-rays, and including, for the first time, we're going to get images of the poles. So this is really something that has never been done before. And we can have also spectroscopy and simultaneous high-resolution imaging. We will have, from a space mission, for the first time, the vector magnetic field of the solar photosphere. So usually these are instruments that are working from the ground, but for the first time we have yes. Okay, I think Lucas tried to say something. Okay,
no,
so please.
No, was it?
Oh, okay, sorry. So please interrupt me whenever you want. No problem. And so we are going to have this vector magnetic field of the solar photosphere with an inversion technique happening on board. And this is really one of the new things that a space solar mission can do. And of course, we are going to image the corona and the heliosphere. The mission summary, so we launched last year, and just for those here who haven't been at the launch, it's really highly recommended. It's a unique experience that I really enjoyed going there. Okay, not only because I worked on the spacecraft, but just because it's nice to see. So NASA launched it with an Atlas V launcher from Cape Canaveral. And right now we are still at what we call the cruise phase. So cruise phase is the phase during which we are testing instruments, and the reason this lasts 1.8 years is because we want to wait to go close enough so that the mission makes sense. So we don't want just to operate the mission when we are still at 1 AU, because that's not why we did the mission. So the nominal phase will start when we go as close as 0.3 astronomical units and even closer. And this will happen next year in March 22. Actually, the nominal mission phase will start this November. So right now we are taking data mostly from the in-situ instruments, and we have also tested the cameras and calibrated and things like that. And the first papers that came out are still with these very first data that are not the nominal data. So the mission really starts next year. And then we have an extended mission. So after these 4 years, that will be another almost 4 years. And this is when we will really get out of the ecliptic, and we will reach finally a latitude of 33 degrees. So this would be the inclination out of the ecliptic, and there we can see the poles of the sun. So the reason we go close to the sun is, of course, because we are going to have better resolution, but also as you go close to the sun, you reduce the relative rotation as you see it from the spacecraft. So if there is a point, which is I think at 0.22 or 23 astronomical units, where the spacecraft would really co-rotate with the sun. Unfortunately, we cannot go to the full co-rotation for thermal reasons, so we cannot get closer to 0.28. But finally, we reduce the relative rotation of the sun by a fair amount, by a fair factor, so that we can really observe the structures of the sun, of the solar surface, as they go around the sun during a complete solar rotation. So actually, we will not really lose them out of sight. Right now, we can see a feature in 10 days, and then it hides at the other side of the sun. And now we will be able, with Solar Orbiter, to observe it for a longer time. So if I can just show a video of this 10-year journey in 35 seconds. So this is the trajectory. So we launched last year. We went very quickly to the first perihelion of 0.5 AU. This was 1 year ago. But if we really want to go to 0.3, we have to wait. And you can see here on this video how progressively we get out of the ecliptic. And so the trajectory gets inclined, and we go at the end of the decade to 33 degrees. But we will already in 2025 reach a high enough latitude to also address the goals that have to do with this high latitude. So here is the latitude and the distance to the sun as a function of time. Maybe that's also very interesting for undergraduate students to see how actually we can apply the third Kepler law directly to understand this diagram of the distance to the sun as a function of time. When you see the perihelion on the very bottom part of this slide, that reaches 0.3 astronomical units, and there we only stay for a very few time, like 10 days out of the 6 months of the period of the orbital period of the spacecraft. So actually, we do two orbits per year. So each orbit has a period of 6 months, and you spend only a few days at the perihelion. And of course, when you are far from it, you spend more. So in light blue is still the cruise phase, and as I said, we are going really close to the sun, close to 0.3 next year. And you also see how the latitude gradually increases. In order to increase the latitude, we are using Venus. So we fly by Venus. So we go very Venus, and we use the gravitational assist to change direction. And we are going to have 7 of these Venus flybys, and we had one already last December, and we're going to have the next one this August. And actually, it's even more interesting because this August we are going to have our flyby, and just the day after us, Bepicolombo will have its flyby. So what will happen is that while Bepicolombo is inside the magnetic environment of Venus, we are just in front of Venus, measuring the solar wind that hits Venus. So hopefully we have a coronal mass ejection. We can really see what happens there with a 2-point measurement. So when we, at the very late flybys, we will go down to 350 kilometers from the surface. This is a quite risky thing. So because temperature is high there, and the instruments will get heated from the albedo of Venus. So for this reason, we cannot go even lower. But okay, this down to these distances we can make it. Well, I hope so. So just also, this is also for undergraduate. What is the sun structure in a nutshell? So we have the core, the radiative zone, the convection zone, and then the photosphere and the environment out of the sun. So maybe just for the core, that this is where the fusion is taking place, and we do have the proton-proton chain that you then have the production of helium, and this is what really gives the energy that is getting out of the sun. Obviously, as you also know, the photons that are produced in the core do not get out immediately, quite on the contrary. And if I go back, so the core is at this temperature of 15 million degrees, but then when we have arrived at the photosphere, we are down to 6,000 Kelvin. So it's really, we do have a very different environment. However, when you get out of the photosphere at higher altitudes, we have the chromosphere, which is already at 10 to the 4 Kelvin, and then we go out to the solar corona that reaches 1 million of degrees, and more so that's for the electrons and more for the ions. So, and this happens on a very small altitude, so what we call the transition region, and there are many things there that we don't understand, and like, how does this happen so effectively? How does this happen at this small altitude, and why does it happen? In the first place. So you get out of the source of energy and you increase your temperature within a very, very few kilometers. So this is how, something that you all know. And then with the solar missions, we mostly observe what happens out of the photosphere, right? So we don't really look at the core, we don't really look at the radiation zone, but we still try to understand, and this is one of the big objectives of Solar Orbiter, how the solar dynamo works. And that is, we want to sense deep in the convection zone and see and get a clue on how it works, how it is generated, and how it changes. And so this is one of the out of the 4 goals of Solar Orbiter, which is to do helioseismology and also helioseismology from the poles, and also by looking at the poles or close to the poles, and also from 2 different points, like from Solar Orbiter, and then combine it with another observation point from Earth. And yeah, so this is also how we can start with a dipolar field, and then because of the differential rotation, these field lines get mixed, and then they can produce, or in theory, they are producing what we are observing, which is a very multipolar, messed up magnetic field all over the surface of the sun. And then you have the sunspots and everything else. And this sunspot cycle has this period of 11 years, which we don't understand why. It's 11 years. We don't really understand how this works. Of course, there are many papers on this. Of course, there are many theories, but clearly, if you ask somebody what is the basic idea behind this 11 years sunspot cycle, I personally I don't know the answer. Yeah, okay, and maybe I will skip this. And then, of course, out of the corona and out of the immediate external environment, you do have these eruptions that can happen, coronal mass ejections that can burst into space and fill the heliosphere, and you all know what are the effects of this, how the interaction happens with the magnetospheres, and also how this affects our Earth, including how the auroral lights are produced, etc. So it is very important as well from the point of view of space weather, but I have to note that Solar Orbiter is not a space weather mission. Solar Orbiter is a mission to understand solar physics. It's not a mission that will help to predict a space weather event. But of course, if we understand, it's already very important in order to improve our space weather science as well. The main idea behind Solar Orbiter, and this is why we have all these instruments, is that we link what we see what we measure in situ around the spacecraft to what happened to the sun. So the problem we have with the solar wind or with the mass ejection or energetic particles is that when we measure them at 1 AU or even closer than that, there are so many processes of diffusion or interaction between different regions that finally what you measure there, you never know where it came from. And so the idea is by getting closer, these effects will not have time to affect the trajectories of the particles or of the solar wind, etc. And so we can really get a better idea to where they were ejected at the sun. So what we do with Solar Orbiter is, for instance, let's say we observe a flare and we have an idea of what the region that generated this flare was by observing at UV and X-rays. And of course, this is what other missions do and what ground observatories do already, right? So it's not something new, it's just that we are going to do it closer and with a better resolution. And then you have this flare, you observe it with Solar Orbiter, and you have escaping electrons that are going to follow the magnetic field lines and reach the spacecraft, hopefully if we are on the right region. And then you are observing this with a Solar Orbiter, and at the same time, you also have a radio instrument that will see the radio burst, and you can really have a holistic picture of of what happened for this specific event. And by being close enough, we want to identify the region from where it came. So this is really not easy. So it's not because we say that we are going to do it or because we are going close that we are really going to do it. We have to be light as well to be on the right region, but also we have models to select what is the region we want to observe at high resolution to make sure that we observe the right region and not the wrong one while we are connected to that other region. So it's quite of a problematic, and we are really we are working on this. So we have four big objectives for Solar Orbiter. The first one is how and where the solar wind originates, and same for the magnetic field. So where does the solar wind come from? So as you know, we have two kinds of solar wind. We have the slow solar wind and the fast solar wind. Slow meaning 300 kilometers per second. Fast means around 800 kilometers per second. And I'm talking about the solar wind, not the coronal mass ejection. So solar wind meaning the steady state phenomenon that is the outflow of plasma that fills the heliosphere, and this goes on all time. And we know from Ulysses that the fast wind is mostly coming out of the poles, while at the equatorial regions we have a mix of fast and slow. But clearly there are, if you ask somebody, where does the slow wind come? Does it come from this active region that I see there, or does it come from the darker regions that we see on this video? Or does it come from at the border of this region? So we really don't know. And this is important if we want to understand how the solar wind is generated. And of course, we have the more basic questions, which is how does the wind get accelerated to high speeds? And this is also very probably linked to the coronal heating as well. The second objective, so as you know, so that was on the wind, which is the most steady state phenomenon. And then we know that the heliosphere is also dynamic, and this is not due only to the solar wind, but also to the coronal mass ejection. So this is our second big objective, which is how do solar transients drive the heliospheric variability? So how do the solar eruptions get erupted, why they get erupted, and how they expand and how they propagate into the interplanetary medium. We don't so again, when we are at 1 AU and we measure something, we only measure a part of it. And for instance, so you have this structure of bright loop, bright core, filament material, prominence material, etc. Or this dark low cavity, low density cavity, and we don't, we never know at 1 AU where we are in. Well, of course, we do if we have multi-point measurements, like we had when the 2 stereo spacecraft were working. Now we only have one of them, and of course we have points of measurements at Earth with other spacecraft, but getting closer will really be a big benefit for this code. The third objective is more specific about energetic particles. So we have 2 major mechanisms of acceleration of energetic particles from the sun. So we do have solar flares where you may, very probably there is some kind of electric field that is involved in the acceleration process. And then you have acceleration, stochastic acceleration at the shocks. So you have a coronal mass ejection that erupts, it forms a shock. And then there you can also have acceleration of particles. So we do know that both mechanisms are at play. We don't know what is the relative importance of them. And then we have some other mysteries about energetic particles coming from regions that should not come. And I will tell you, I will show you something about this later. Or actually right now. So in principle, when you have ejection, acceleration of energetic particles, these particles should follow the magnetic field line when they get out of the sun. So they do a spiral and they follow the magnetic field line. So if you are on this plot, if you look at the middle where we say A, B, E, M, so these are spacecraft. So A is stereo A with this red line. So if you have let's say an ejection of particles at a given point from the sun that are supposed to follow the spiral that links to the stereo spacecraft, and this is a spiral in red there for the stereo A spacecraft. That's fine. Then you observe it at the spacecraft and you are happy. Now what happens is that we have other spacecraft around the sun, like stereo B or the Earth, which is there with the green spiral, or we have another. We have Messenger at Mars. This is M. This is the orange. If you can see the colors, and there are events that are measured everywhere. So how is this possible, right? So you have an ejection at a point, and there, and from a given region, and this should go to a given spacecraft. So is this diffused that much that it fills the entire heliosphere all around 360 degrees around the sun? Or is there something really that we don't understand on how the magnetic field lines are just out of the corona? Maybe that's the answer, that we don't really understand. And if you look at these events that are called widespread events, and you see them in not only in one category of particles, but all particles, electrons, ions, helium, you do have only 36% of these events, if you do some statistics, that are measured from only one spacecraft. So then you have big numbers of these events that are measured by other spacecraft as well. This is one of the things that we don't understand for energetic particles, and this has to do obviously with how they are transported, but also how the magnetic field looks like out of the corona. And then the fourth objective is the solar dynamo. So this is really an objective that needs for us to go out of the ecliptic to take a big clue. So what we don't really know, as you see from the plot right on at the bottom right, we don't know actually what the convection zone looks like at the poles. Right, and this is very important if we want to understand the dynamo. So what we can do with Solar Orbiter is, first of all, to do helioseismology by looking at the poles, but also, as this plot in the middle shows, is that we can, if we want to probe deeper layers, we can do what's called, so we can do combined helioseismology by observing on one part from Solar Orbiter at the poles, and then from, let's say, GONG at 1 AU, and then you can really see how the waves that are propagating in the deeper layers. So what we did up to now, so as I said, we've been at the first Venus GAM last December, and now we are going to the next Venus GAM that will really help us get out of the ecliptic and also modify the trajectory so that we go closer to the sun. We are going to our first perihelion at 0.32 astronomical units next March. So again, what I'm going to show as first results are really results that have been taken during the period that is not yet the most interesting for Solar Orbiter. So let me show you the spacecraft. May I please ask to Yanni or Maria to alert me when I have 10 minutes left so that I'm not exceeding the time?
Yes, yes, of course.
Okay, thank you very much. So the spacecraft is a very busy spacecraft, so with many instruments on them. The first thing, the most important, is that we had to protect from the sun. So we have a heat shield in front that makes that the temperature, so actually in front of the heat shield, the temperature when we are at the closest perihelion is around 550 degrees Celsius. So, and we want that our instruments behind the heat shield operate at room temperature at, let's say, 20 or 30 degrees. So within a very few centimeters, tens of centimeters, we go from 550 to 30. So, and this huge, and achieve this huge gradient of temperature is really something, is really a technological challenge. And this is maybe the most challenging part for the people who build the spacecraft. I didn't build it myself, so I'm not sure I can give you many details on this. So what we have is a multi-layer carbon fiber composite and of titanium that uses different techniques in order to evacuate. Okay, first of all, to stop the heat, but also the remaining gets evacuated to from the sides, and then behind this you have another layer that is still blocking the heat from flowing down to the instruments. The challenge, the real challenge, is that it's not enough just to put a heat shield and block out the heat, because you want to look at the sun. So you want to have telescopes that are looking directly to the sun. So we have this feed through, so these holes with doors that can open and close, and there you can, so the challenge is how to make sure that the part of the telescope that gets out is not one taking all the heat again to the backside of the spacecraft. And the other challenge is how do you reject the sunlight, because you don't want all this sunlight to make that your pictures are not meaningful. So that's so actually it's not a huge spacecraft, but it's quite big. So the size of it, so the spacecraft, like it's 2 meters by 2 meters, and then you have the solar panels that go 18 and 18 from no, actually 18 is from one side to the other. And you also have 3 radio antennas. These are electric antennas for plasma diagnostics that are 6.5 meters long. So you have one on the top and then 2 out of the 2 coins of the spacecraft. And behind that, we have an instrument boom where we have plasma instruments that have to be far from the spacecraft in order to get meaningful data. So these were the engineering challenges. Maybe I won't spend more time on this. So this, you can read, there are many articles on this on the web about how this was done and how this solar heat shield is made. Other challenges that we had were, for instance, we have on every spacecraft what we call the reaction wheels, which are there to stabilize the spacecraft and make sure that it has the right orientation. So these wheels are usually built with many magnetic parts, and they are spinning. So this is very bad when you want to measure a magnetic field or an electric field. And this had to be really shielded, but then if you shield them, you add the mass. So it's not an easy thing. Another challenge was that we have the solar panels that can get charged. So typically the energies of electrons in the solar wind can be from 1 eV to 10 eV. And the spacecraft charges to 5 to 10 volts. So if you want to measure an electron that has an energy of 1 electron volt, but you have charged your spacecraft to 5 volts, and then you're not going to measure the real energy of the electron. So we had to make sure that it's conductive, and also that the solar panels get this surface that makes it conductive, but that at the same time also always it doesn't get heated, etc. So there are many system engineering problems that had to be solved, and in most of the cases together with the scientists, because every time that the engineers were doing something on the spacecraft, this affected science. And it's not just a telescope where we look at the sun, it's many other instruments that we don't want to affect. We have many instruments. Maybe I will skip the slide as well. So from many countries, and I will go into the details right away. And one of the biggest challenges was also to coordinate people and scientists who from so many countries, from the US and Europe, and from industry and many universities. So actually the problem with Solar Orbiter is what our astronomy colleagues make fun of us, telling us that this is a Christmas tree. Christmas tree means you put whatever you have on it. So, and that's true. So we try to have many instruments, and we have a very limited space. And this is also another reason why it's challenging and complicated to satisfy everybody and to do things. So the solar wind in situ measurements, we measure the magnetic field, radio and plasma waves, the particles, and the energetic particles. So the particles of the solar wind, which are low energy, so 1 eV, 10 eV, and also energetic particles. Energetic in solar physics, we call when you are higher than 1 keV, but you can go much higher, but we don't go that high either, like in astrophysics. So energetic particles. So we have instruments that can detect up to 1,000 MeV per nucleon, but from as low as really 1 keV, and this for electrons, protons, and higher and heavier ions. And we look at different parts of the sky, so that you can also look. Okay, the most important, you don't look directly to the sun, because that's not where the particles are supposed to come, because they're supposed to follow the magnetic field lines. But we also look at other directions of the sky, so that we make sure that we measure the background, and also particles that may come from a more complex magnetic field configuration. We are right now at the minimum of the activity of the solar cycle, so we don't get too many events. However, as we go closer, we get more, and this has already been observed by the Parker Solar Probe, and we did have many, let's say, events during the first year of orbit. And also we have been through the fragmented through the tail of the fragmented comet Atlas. This happened just one day before we started taking measures, and I mean officially, but we already had the instruments on. And we have measured dust and waves from this comet, and there is a paper that is still under review in A&A, and hopefully it will come out soon. And we also measured energetic particles in that environment as well. The other very important instrument is the magnetometer. So the magnetometer measures the magnetic field around the spacecraft. So it's a very basic principle. So you have a coil that is moving in a magnetic field, and this induces current, and then you measure this. The problem is that the current is really very, it has to be very, it is very low, so you have to be very sensitive. And the other problem is that you have to be you have to be as far as possible from the spacecraft, so that you don't measure any magnets or anything, any disturbances from the spacecraft. So this works very well. So the magnetic field that we are measuring in the solar wind is nanoteslas, and it can go up to 20 nanoteslas if you are in a magnetic cloud which has a strong magnetic field. And you can see there on this plot, we can see that the magnetic field has a structure between 19 of April to 20 something of April. And because this is a clear signature that we are going inside a magnetic cloud that has a magnetic field rotation. One of the components is rotating. The other thing that we can do we already did with the magnetometer is that we observed a coronal mass ejection that was imaged by stereo, which was at the bottom of the left panel, and then this coronal mass ejection, which was just imaged going towards one side, we measured it in situ by solar orbiter, and this shows you how we can take advantage of the different spacecraft in the heliosphere to do coordinated studies. And so that was just the first coronal mass ejection measured, and then we can build models that are instructed by the data that we are taking with the spacecraft. The other instrument is the radio and plasma waves. There you have antennas, and search column magnetometer is observing the electric field and the magnetic field. And you have in plasma, you have a huge family of different kind of waves that you can measure, including electrostatic waves, magnetic and electric fields, and there. So this plot just shows you that we have the sensitivity that we need in order to study everything that has to do with the turbulence, with the radio bursts, Langmuir waves, and so on. So for those who know what that is and are interested. The other instruments are the plasma analyzer. So we have an analyzer for low energy electrons, less than 5 keV, protons and alphas, and heavier ions. And this is a first. So the heavier ions, we are going in the inner heliosphere to measure them for the first time. Parquet Solar Probe doesn't have such an instrument, and it's very important when we want to connect what we see at the sun, because when you do spectroscopic observations of the sun and you can identify what are the ions that you see there, and then you also identify the same ions at the spacecraft, so then you are more confident on where this came from. Well, it's not that simple. You need more, but it is really a very important element to measure, and also for explaining heating and other processes, plasma processes in the solar wind. So this is for the in-situ part. Then we have the remote sensing part. What I was saying, the thing that we are going to do for the first time on a spacecraft is the visible light polarimetry. So we are going to measure at the visible light. So we measure the magnetic field. Actually, we are going to provide maps of the magnetic field vector and the plasma line of sight velocity in the solar photosphere. So this is the photosphere, and when we are going to do high resolution images at the closest perihelions, we will have a resolution of 200 kilometers. So up to now, we have only achieved 400 because we've been at 0.5 AU. And this is a first. So this resolution is a first and while from space, while doing at the same time the inversion, and you get the magnetic field vector. We have other telescopes for UV imaging, and same. So we have a telescope for all these wavelengths a telescope that takes the full image of the sun, and then we have high resolution imagers that are looking at specific region that we have to choose if we want to study it. And then we have one at UV and the other at the Lyman alpha spectrum for these UV images. And again, we can go down to a few hundreds of kilometers of resolution of spatial resolution. And this is how we got to these images. This is how we can, so some examples. So these are images from 0.5 astronomical units. And we can see, of course, as I said, where does the wind come from, and try to see these regions at high resolution. But also what is really cool with solar orbiter is that we can see the far side of the sun. Okay, what some people like to joke about, the dark side of the sun. So you see something, that a feature from when you are at the other side that you cannot see from Earth. And of course you can do this with stereo, but not at this resolution or that close. So we can really follow a feature now. We have this possibility to follow a feature that goes at the other side and still be able to observe it for a long time.
So, Yannis, you have
yes?
about 10 minutes left.
Okay, thank you very much. I have to be quick. So we got so at this distance, when we just turned on actually the instrument, the UV instrument, we saw what we call these campfires, which is maybe not something completely new because this has been observed before. So this looks to the nanoflares that have been discussed and predicted many times ago. So what is really new is that we observe this at these wavelengths. And the other novelty is that we see these small eruptions, this flow, this small. Actually, we don't know what it is. That's why I cannot really describe it. And we are still at the very beginning of this, but we see them everywhere on the sun, including on the quiet sun. And this is maybe one of the things that we really have to, that we don't understand, that we have to explain. So so this was also some kind of a nice outreach, or not outreach, but publicizing of the science we do. And we are really happy that this works. It's not every day that you see astrophysics on the first page of Financial Times, which has nothing to do with astrophysics. And so that just to say that it's important that when everybody can do something to put astrophysics and science in general on the front page, it's great. We weren't expecting this, by the way. Of course, we don't just take images, we are also doing science. So we have spectrometers, so we can really, we have many UV diagnostic lines to understand what's going on in the sun. And we've seen also these peculiar brightenings that are seen in all temperatures. So you see them in different lines, so you know that these are at different temperatures. And they go up to 600,000 Kelvin. So these outliers that are really there and stay there. And they are somewhere in the transition region network, which is the interface between the chromosphere and the corona. And this is also something that we haven't seen before, at least not at these lines. So yeah, so we can also look at the Doppler shifts and get an idea of how the material is flowing, but that's not something new in just that we do it closer enough. We do have a coronagraph, so we see what goes out of the sun by just making an artificial eclipse. And this is called METIS, and I know that there are many Greek colleagues that are participating in this on this instrument and the analysis of this data. And we also have an X-ray imager. So I'm sorry, I will go a little bit fast on this, just to make sure that I cover everything. We have an X-ray telescope that is now working all time, so that we are sure that we're not going to miss any flare. And so together with the UV that's mapping the underlying region that gives birth to a solar flare, we can also map it at X-rays, and with a very good time resolution down to 0.1 second. And then we have this wide heliospheric imager, these things that you have already seen with SOHO or with on stereo, that can map a big region of the heliosphere. So you see there actually the field of view, so it goes from the sun to the earth and beyond. And this is really a composite image of using this detector that we took from Solar Orbiter, where we can also see a comet, Mercury, and the Earth. And this is a simulation of how this works, how these different fields of view are going to map the ejection of the solar wind coming out and of the coronal mass ejections. Now, the big challenge here is that it will be the first time, and okay, this has already started with Parker Solar Probe, that we are going to analyze these images while moving. So usually solar physicists are used to looking at an image from a fixed distance. But now we are moving. So what do we really see while we move? It's not clear how to do this analysis. And you probably all know Angelos Voulidas and Spiros, Patrakos, they are really working on this. Yeah, and this is a cool image that we got from this instrument that had Venus, Earth, Mars on it, and including Uranus. Sorry, just this is like the pale blue dot image that Carl Sagan liked to show, and it's quite rare to get images with all these planets on it. And okay, this was nice too, also for outreach reasons. Okay, what I have to say here for those who are solar physicists and are interested, all the data are public, and they get public very quickly after reception of the ground. So we only keep them for 3 months for calibration and making sure that they are okay, up to 3 months. So the instrument teams have to give them always at the latest 3 months after they get them. So we already have this Solar Orbiter archive when you can go and look at the data and do science with. And we have a web page that where you can see, so this is a screenshot from today. We are 499 days from launch, and there you can see where the Solar Orbiter is and latest news, and then go really and see what we plan for the next decade. Tell us what to change if you want, if you have great ideas, and you can see the publications and the data. Okay, the very last thing is to say that, so I said you can influence operations if you want, but it's not an easy thing. So solar physicists, again, who are used to SOHO or Earth ground observatories or other kind of spacecraft, SDO, for instance, they are used to high telemetry. But this mission is not like is not what we call a joystick mission. So you cannot really operate it real time and say now, oh, look at this active region, or look at this flare, or okay, look at this region because it's more interesting, and really change it. Actually, we are many times at the other side of the sun. The communication with the spacecraft can take up to 15 minutes. And so we cannot really do whatever we like. and we are far, so really we need big dishes to get out the data and to communicate. So we really have to plan carefully, and this is what we've done, and we are doing it. So we have big discussions on what we do every orbit and every year. So if you want to participate and you have ideas, again, let us know. So just to let you know that, so I'm in charge of this, so just let me know and we can discuss. And so, yeah, it's not a joystick mission, so it's most like a interplanetary mission. So that's just like a Cassini here. And solar physicists are not really used to this. So we need to plan just like we're going somewhere where something might happen and we're not going to go back. So we really need to make sure that we are not going to miss any opportunity. And it's a very different philosophy, but also Parker Solar Probe has this philosophy, but with the difference that they don't have cameras. So for us, the big problem is how to optimize the telemetry so that the images that we do the meaningful observations, and really we take advantage of of the constraints we have and make the best. And yeah, so just before I finish, so this is how actually we launched Solar Orbiter just 1 month or a few weeks before the lockdown for the coronavirus. And so we thought that everything was going to be great, but actually, so these were the meetings just before at launch. And then this is how our meetings are right now. So we are all on Zoom. And of course, you are all on Zoom, and you know what I mean, but this is also the very first mission in the space history that has been commissioned, calibrated, and done the very first phases during lockdown. So actually, we operated everything from home, and this is really, this is a first. And that's all I have. Thank you very much. And just before I see Yannis that has turned on the camera, sorry for being late. I would like to take advantage of this seminar because I am talking to the university, and so I hope there are many young people there following us. So I would like to tell about my other job that I do in my free time, which is being in charge of the ESA Science Research Fellowships, which is a very competitive postdoctoral program, and we offer around 8 to 10 positions per year. So it has a it's very competitive. So actually it's not easy to get. It's a little bit harder than the Marie Curie fellowships from the competition point of view, but actually it's very prestigious if you get. So, and the big advantage is that for 2 or 3 years, you can do whatever you like. So you are independent, nobody tells you what you do. So if you have a proposal and you have an idea of what you want to do, then this is really a great opportunity. So if you want to know more about it, let me know. You can go to ESTEC or in the Netherlands, to ESAC in Spain, or at the Space Telescope Science Institute in Baltimore, where we also have an ESA team if you're interested in JWST, etc. And the next call will be in September, October. So if you are interested, let me know as well. And yeah, sorry for having added this on top of Solar Orbiter. And that's all from my side. Thank you very much.
Okay. Thank you very much, Yanni. And thank you very much for this very insightful presentation of the Solar Orbiter mission. I learned a lot, really, I have to say. It's indeed an amazing mission, and we are all looking forward to the breakthrough results that will come out of this mission. And also thank you for bringing this information on the ESA Research Fellowships. It's very useful information for our young scientists. So